welcome back. In the last class, we did the degrees of freedom. We understood what it is, how a degrees of freedom of a serial robot or a general mechanism can be calculated. So we also did transformation matrices, and we understood how a rotation matrix works, how a translation matrix works. So moving ahead further, now we have built up enough of prerequisite to do forward kinematics of industrial serial robots. So let us begin with that. So in today's class, we'll be doing kinematic transformations further, and we'll be doing forward kinematics of industrial serial robot. Okay, so we'll start with link and joint parameters, that is DH notation, which is commonly known as, and we'll go ahead with DH parameter table build up. We'll start doing creating forward kinematic matrices, and we'll do some example problem as well today. If time permits, we'll do 2 and 3 degrees of freedom. Okay, so let us move ahead. So yes, so what exactly is forward kinematics? Forward kinematics is something like you are given a robot and you know its joint angles. So you know its joint angles. So you have a link, you have a joint, you have a link, you have a joint, and that serial finally it terminates at a place. Okay, so if at all you want to go somewhere, you have some joint angle which is to be put to the joints. So provided you know your joint angles, where is your arm? Okay, where is your arm and how is it oriented also? So that is what is to be found out. So that type of problem is known as a forward kinematics problem. So it is defined as given the individual joint displacement oblique angles. Why displacement? Because the joint can be a rotary joint, it can be a prismatic joint also. So in case of prismatic joint, it is displacement. In case of angular joint, it is angles. Okay, so solving for the end effector pose is forward kinematics. Pose means position and orientation. You are going there and you are orienting there in a particular way. So we'll see when we'll actually do it. So steps for doing forward kinematics are all as follows. So you initially will understand the link, joint, their parameters. We'll try to parameterize a whole of your robot link, your system, so that it is easy to define, relate them using some notation. Those notations are popularly known as Dhanbad notations or Dhanbad parameters. Okay, so we'll place DH frames also to different joints so as to relate between those two joints. So that is known as a DH frame. We'll create DH parameter table, Dhanbad parameter table. We'll see when it comes. Okay, and forming individual link transformation matrices. We'll form link transformation matrices for all the links which are there, which are connected one after the other, and finally we'll perform direct or forward kinematics. So these are some of the steps which are necessary to go through before we actually do forward kinematics. So yes, so link and joint parameters. So structure of the link, normally they have a link with two ends. Okay, so one of the end is connected with the previous link which is there in the series, so that is ending with a joint also. So this is a previous link, this is a previous link, I minus 1th link. Okay, so that has ended with a joint I. Okay, this joint I actually connects to the ith link, and finally this ith link also terminates with a frame which is attached to this, which is called as I plus 1th joint. So this joint will further connect maybe some other link in the series. Okay, so it may go ahead like that. So it starts with I minus 1 link, I minus 1 link ends with ith joint. On ith joint, ith link is placed, ith link ends with a I plus 1th joint on which I plus 1th link is fitted. Okay, so these are the joints. These are the joints. This is one axis, this is second axis, and so on and so forth. So that keeps on going. So these may be a revolute kind of joint, or it can be a prismatic joint which can move in this direction. So next link which is connected to this may move like this. So in either way, this axes are all placed with z axis. So they are all placed conveniently with z axis. So this is zi minus 1. Okay, zi minus 1, that is the joint axis. Okay, and this is link I, and then you have distal end, that is zi. So this is zi. So this is the part of a frame which is attached over here. So this is the part of the frame which is attached to the link I. So that is here. Okay, so this is part of the frame which is attached to the link I minus 1. So this is frame I minus 1. This is frame I. Got it? So this is how links are all made. So this is distal end, this is proximal end, the nearer one. Okay, and this is joint axis. These are joint axis. Okay, so yes, this link now becomes the part of a serial chain system. Okay, so you should note that the joint axis about which link I moves is attached with zi minus 1. So you see zi minus 1 as I have just told. Okay, so now let us formalize whole of the link with different parameters which actually define a link. Okay, so starting with that. So first parameter is known as a joint offset. From now on, I will be denoting that using di. Okay, so di is the distance from the origin of the I minus 1th coordinate frame to coordinate frame OI minus 1 to the intersection of the zi axis with xi axis along zi minus 1 axis. So reading it may be quite difficult to understand. Let us look at the figure directly. So where is it actually located? So let us say you have two links which are connected. See my hand. So yes, this is one of the link. Next link comes here. So they are dislocated by both the links. This link and this link, they are dislocated by some distance. Okay. So the axis which was there was z axis, on which you have another link which is connected and that moves. Okay, so distance moved along zi minus 1 because this is the link which is ending with the frame zi minus 1. Okay, and you have another link that comes on top of it, and they both relatively move. Okay, so link I moves with relative to link I minus 1. Okay, so that is the joint. So this is the joint. Okay, so there is some distance between those two links. They are calculated as, so this is your frame OI minus 1. From here to, this is a common axis which intersects both of them. So this is your xi x axis, okay, which is fitted at the end of the link I. So this is part of the frame I which is fitted at the end of the link I. So this is there, and this intersects zi minus 1 over here. Okay, over here, and this is your distance between OI. This was the frame of the previous link that was ending here. So this is your frame. So from this frame to the point of intersection of xi and zi minus 1. So this is the offset which is there. So this is the offset. Got it? So you have two links which are connected like this. So offset between them are measured along zi minus 1. Measured along zi minus 1, and it is the distance between OI minus 1, that is this frame, and point of intersection of xi and zi minus 1. So that is this location. Okay, so these two are the points between which it is measured. Okay, so moving ahead, this is joint offset. So now the next important parameter, that is the joint angle. In case of revoluted joint, this becomes the joint variable also. This may be a variable because both the links, they move relative to each other. Okay, so there is some angle between those two links. So this is the actual measure. So where it should be measured, how it should be measured, we are coming to this. So this was my final point where your x-axis was intersecting to z-axis. So this was the point. So yes, this is your xi axis, xi, and the previous frame ended somewhere like this. So previous frame, it ended here. So this was xi minus 1. So about this zi minus 1, look carefully to the figure where I am drawing. So this is your zi minus 1. So this is the line. Okay, so about this line, if you look from the top, if you see from the top, there is some angle between xi minus 1 and xi. So this is your xi. So angle between xi and xi minus 1 is theta I, and this is your point through which zi minus 1 is passing through. Okay, so you got it. So this is the angle. So theta I is the joint angle from xi minus 1 axis to xi axis measured about zi minus 1 axis using right-handed coordinate system. So if it moves counterclockwise looking from the top, it is positive. Okay, so it is measured like this. Got it? So this is your second parameter. Fourth one is the link length. So it is actually the distance between zi minus 1 and zi. Zi is fitted at the end of this link I. Okay, it is part of the frame OI. It is part of the frame OI. Okay, so zi is there and xi is there. So xi is also the part of the frame. So xi is here, zi is here. Okay, zi is here. So this is it. This is the point, and there is similar point which existed here also. So this is your zi minus 1. So this is your zi minus 1. So distance measured along xi axis, between the axes zi minus 1 and zi is link length ai. So here is your link ai. Got it? So this is known as the link length. Okay. Okay, so now let us move ahead. So what is twist of a link? As rightly said, the name actually speaks. So this is angle between zi minus 1 and zi. Okay, so it is angle between zi minus 1 and zi measured along xi axis. Counterclockwise is positive. Okay, it also follows right-handed convention. So yes, as per the thumb rule, counterclockwise is positive. If you go like this direction is your x-axis. So that is your angle. So this is your alpha I. So it is zi minus 1 and zi axis measured about xi axis. This is known as twist angle. So 4 parameters are there. So this were the 4 important parameters, and this is what fully defines your link. So the first 2 parameters, these 2 parameters which I have noted here, ai and alpha I, are link length and twist angle. So once the link is made, okay, it is maybe a twisted one. So it is, once it is twisted, it is forever twisted for that particular link structure. Okay, so this defines the structure of the link. Okay, alpha is the twist, length is the distance between the 2 axes which are there. One is about which the link itself is moving, other one is the frame which is attached to the link itself, that is the ith frame. So And these two parameters di and theta I are joint parameters which determine the relative position of neighboring links. Okay, so two of them were offset by di distance. In case of prismatic, di is the joint variable. In case of revolute joint, theta I is the joint variable. Got it? So these are the two parameters. Okay. Okay. Now let us form a homogeneous link transformation matrix. Now we know the two frames which are there at the beginning of the link and at the end of the link. Can I find out the relative transformation between these two frames? So that is what is a homogeneous link transformation matrix. Okay, once DH parameters are assigned, homogeneous link transformation matrix may be derived by series of operations starting from AI minus 1 AI, it is known as AI minus 1 AI, starting from I minus 1th frame to ith frame. Okay, so that is it. Or we'll be simply calling it as AI instead of calling it as AI minus 1 AI. Okay, so let us see how we'll go for it. So yes, so these are the four things that we did just now. So first thing that we did, moving from OI minus 1 to OI, how we went from OI minus 1 to OI? First thing that we did is we moved by a distance DI. Moved by a distance DI along ZI minus 1. Okay? Along ZI minus 1. So this is the first thing. We did translation about Z. We came till this point. Now the second transformation. Now the second one. What we did this time is we have already reached here. Now we are still aligned along this. So now we have rotated by an angle theta I and we came to new direction that is given by xi. Okay. This is there. So this is your second one. So you have moved, the first one you did was this one. The second one is moving from this to this by an angle theta I about Zi minus 1. So this is rotation about Z axis by an angle theta I. You came like this. Now what to do? So this time I have already moved like this. I have already rotated like this. Now I'll translate from this point to this point by a distance AI, that is the link length, so that I reach till this point. So this is a translation by a distance AI along x-axis. So this is translation about x-axis by a distance AI, and you reach till here. Are we done? No. We still have something remaining. Okay. So both the Zi and Zi minus 1, the new frame is aligned still. I have to bring it to Zi actually. So what now I have to do? This time I will be rotating about xi axis by an angle alpha I and will bring Zi minus 1 to Zi. So this is the final transformation. So four transformations are there. First, displacement along Zi minus 1 by a distance di. Next, rotation about Zi minus 1 by theta I. Next, translation along x-axis by a distance ai. Next, rotation about xi axis so as to finally align to Zi and reach till OI. Okay, so this is your four transformations. So finally, in order to reach from here to here, you have to do these four transformations. So four consecutive transformations which I have just covered is this. This is translation along Zi minus 1 axis by a distance di. So this will be your transformation matrix. Next will be rotation about Zi minus 1 axis by an angle theta I. So Zi theta I. So this is your rotation matrix. And third one is translation along xi axis by a distance ai. Okay, so this is it. And final one is rotation about xi axis by an angle, twist angle, that is alpha I. So this is rotation about x axis, alpha I is here. So this is your 4 transformation. Now look carefully, where none of them were global transformation. That means first transformation was dislocated from the starting frame, then it was a relative rotation, again relative, finally you reach to the end point. Okay, that is OI. Okay, so all were relative transformations. Only the first one was principal axis transformation. Okay, you started from your principal axis, over here it is I minus 1. Next transformation was a relative transformation. So that is why all that 4 transformation matrices will be post multiplied. Okay, so this is your first one, this is your second, this is your third, this is your fourth. If you put them all together, finally you will get a linked transformation matrix, homogeneous matrix, which says I minus 1 to I. It will take you from location I minus 1 to I. So this is your location, relative location of ith frame from I, and this is your orientation change. Okay, this as usual it is 1, these are 0. So this is your homogeneous transformation matrix. So this is your link transformation matrix. Okay, so now we'll move ahead. Please note there are few things here. So any matrix, transformation matrix, if it is I with respect to I minus 1, if you have to do inverse transformation, you have to reach, otherwise that means this frame is expressed with respect to this frame, ith with respect to I minus 1. If I say I have to represent this frame with respect to this simply will become inverse. Okay, so this is it. Got it? Okay, so theta I is the only variable in case of revolute joint, everything else are constant. Di is not a joint variable in case of revolute joint. So once 2 links are placed, that is always having same offset. Okay, so for prismatic joint, Di is variable, whereas Ai becomes equal to 0. Link length becomes equal to 0, and you can only move along Zi minus 1 axis by a distance Di. So this is there. Okay, so we can simply use the previous transformation matrix, just substitute Ai is equal to 0 and you will get this. Okay, so this is it. So now concatenating all the transforms. So let us say you have first link, you have second link, right, you have third link, okay, and so on so forth. You have multiple links here, and this is started with the 0 frame which is mounted at the ground. Okay, so this may be Z axis, this is Y axis, so it can be like that, and there are other frames which are coming as 1, 2, 3 and so on so forth. So each link has their own transformation matrix from starting to the ending frame. Okay, from here to here. Okay, so that is it. So if it is link 1, for link 1 it is 0 to 1, for the link 2 it takes you to 2, it starts from 1, for the third link it takes you to 3, it starts from 2, likewise. So finally if you want to reach here, so you have to multiply all of them together, so concatenating them, so 0, 1, 1, 2, 2, 3, finally you have to go till I minus 1 I. So with respect to ground, any ith link frame, that is the frame which is finally attached to the ith link, so if you want to reach there, you have to take product of all of them. So this is product of all of them. So this is it. So this is how you reach till the end point of a link. Here in this case it is third link, I is equal to 3. Got it? Okay. So let us now formalize the way we are going to draw a robot. We cannot draw a complicated shapes, so rather we will be representing them using link which is something like this. So This is what? This is a joint. If it is a revolute joint, we will represent them using cylinder with z axis placed like this. Theta I is the joint angle. So you may have a link which is something like this. So on top of it this, you will have another link that goes here. So this is your joint. Okay. And another one could be simply like this, in which you have a link fitted with a prismatic joint like this. So you may have another body which can move like this. Okay. So this is your prismatic joint. Got it? So these are the two important joint symbols. Okay. So now in summary, DH representation, what it did, so it is a matrix method for systematic establishment of link coordinate system of an articulated chain. Articulated means it is a serial chain, fitted one after the other. Links are fitted one after the other. Okay. So next is, this results in a 4x4 homogeneous transformation matrix, a I minus 1 I, that relates ith link to the I minus 1 coordinate system. Okay. And I can start from 1. Okay. So least value I can take 1 to number of degrees of freedom. Okay. And the end effector may be expressed with respect to the base. If you can do concatenation of all those matrices, of all the link matrices, so ultimately what you will get is T0 to, starting from base frame 0 to the end effector frame. Okay, so the final transformation matrix will have this having end effector position, end effector orientation, 0, 0, 0 and 1. So it is like this. Okay, and when the joint activates, joint I activates, link I will move with respect to link I minus 1. Okay, and ith coordinate system which is fitted at the end of link I, that will move along with link I. Okay, so these are the steps to assign DH frames to a serial chain system. If you are having a robot which is like this, okay, so how to assign coordinate frames? So can this be X, this can be Z, again next one will be Z, where all the X, Y, Z will go. Only thing that you know now is axis of rotation, they have Z axis. Okay, they have Z axis, that's all. So these are the steps. So that is the reason it is smiling here, because it is very difficult to mug it up. Okay, we'll do by practice. So today we'll do one small example, and you will see it is not that tough to remember this also by practice. We'll do 4 or 5 examples in this module, and hope you will be very much familiar with this. Okay, so yes, these are few more steps which are here. Forget all these now, need not to mug up, need not to repeat here. So let us quickly begin with 2 degree of freedom planar robot. So what I actually want to do here, I want to place the frame 0. I want to place every link with a frame, and I want to find out the transformation matrices, link transformation matrices, that I can do concatenation, and finally I can reach till end effector. Got it? So let me see if I can explain you well using this figure. So this is a robot. So you see it can move. So let me just quickly move it so that you can understand how this link is connected, how the links are connected. So you see it can move like this. So you have first link with one color fitted with the ground frame, red and green it is showing. Okay, and you can simply move it like this. So 2 joint angles are there. You can just move one of them, okay, or you can move both of them. This is only moving the second link with respect to the first one. So if I want, I can just move the first joint without moving the second one. Okay, so this is how it will move. So I have just commanded it to go from 0 to 90 degree. First joint. So this is what is a 2 degree of freedom robot will look like. So this is the figure which quickly represents the same structure. So this is your joint. So you know the first axis which was there. Okay, so this is your first axis. So I'll use a convention from now on. So I'll use red color for x-axis, green for y-axis, blue for representing z-axis. So that will be convenient. So yes, let us quickly go and put those frames here. So yes, this is your z-axis about which first link is moving. It is out of this plane. So in order to make it visible, I have just drawn it like this. So about z-axis, z0 axis, that is attached to the ground. Okay, that is a first frame is always attached to the ground about which first link will be moving. So this is your first frame named as 00. So z0, x0 and y0 can be conveniently placed the way you want your robot's end effector to lie in whatever space. Okay, so accordingly you can put x0 and y0. So if it is all positive you want, so this should be x0 here, y0 here. Okay, so it follows a right-handed coordinate system. X cross y should be z. So yes, so z0. So theta 1 will be measured. So first link. So this is your first link. Okay, that is running on. This is your I is equal to 1. It is running on z0 axis, and this itself is ending with a frame on it. So that will be given as z1. Why z1 is like this? Because that becomes the axis of rotation for the second link which is here. This is I is equal to 2. Okay. Finally, that also will be ending somewhere. So this can be just a dislocation of this frame. You can put it here. So this also, fortunately, I have put it like this. It can be placed any other way. So this is your second frame which is at the end of link 2. So this is your link 1. This is your link 2. So link 1 ends with Z1. Link 2 ends with Z2. Okay. And Z0 is the frame about which link 1 rotates. So you got it. So distance between, you see this link, this system is completely planar. So distance between Z0 and Z1 is your link length. So that is link length given as A1. Okay. Similarly, distance between Z1 and Z2 is your link length 2. So this is A2. As it is a planar system, so there is no dislocation along, offset along Z axis. Okay, so both the systems are exactly lying in the plane, not like this. So there is D1 is equal to 0, D2 is also equal to 0. Only thing that remains is A1 and A2, those are the link lengths. There is no twist. You see all the Z axes are parallel. So you have a link with both the Z axis about which it is rotating, and this also has a link frame. Okay, so both are parallel to each other. So there is no twist in between. So there is no angle between Z1 and Z2, Z0 and Z1. So alpha 1 and alpha 2 will also be equal to 0. Okay, so D1, D2 is 0. Alpha 1, alpha 2 is also 0. A1 and A2 are link lengths, and what remains is joint variable. Theta 1 and theta 2 are joint variables. Okay, that is the only variable. So same thing is written here. This is how we can put the frames. Angles will be measured in right-handed coordinate system. Okay, so that's all. So now I can quickly put my DS table with the parameters that I have just said. So for link 1, AI, this is your link length, it is A1. Okay, similarly for link 2, link length is A2. Alpha I for both, because there was no twist, there is no angle between any of the two consecutive Z axes. Okay, so alpha 1 and alpha 2 is equal to 0. Similarly, this link is completely planar, so D1 and D2 is also equal to 0. These are joint variables. Okay, these are joint variables. Okay, so now this is your DH parameter table. Okay, We have reached till here, so DH parameter table I have just transferred it here. We already know the link transformation matrix. So it starts from I minus 1 to I, okay. So if I put I is equal to 1, so that is your first one, that is with respect to 0, and I will put all the values which are here. Similarly for the second one, which is with respect to the first one, so I will put this one and I will use all these values to obtain that in this matrix. So this is the one which we just now derived, link homogeneous transformation matrix. I will substitute these values here and I will get exactly to these two transformation matrices. Got it? So these are the two. So quickly I have just put them here. So these are the two, and taking product of them will take me to the end effector point. So this is your end effector point. So if I have taken product of this, finally I got what? 0 to 2. So that tells me the end effector position. One can quickly at least derive this one quickly. So what is that? You just see it here. So it is A1 cos theta 1, and this distance is A2 cos theta 1 plus theta 2. Got it? So sum of them is your x coordinates. So this is here. Similarly, y can be obtained as A1 cos theta sin theta 1 and A2 sin theta 1 plus theta 2. Got it? So that is here. This is y, and z, because it is planar, so z is always equal to 0, and this. So got it? And you can quickly verify even the rotation matrix, at least in this case. So this is your rotation matrix. You see, this is a rotation matrix about z axis by an angle theta 1 plus theta 2. So end effector frame, you see, it is combined angle is theta 1 plus theta 2. So this frame, end effector frame, is now rotated with respect to ground frame, that is x0, y0 by an angle theta 1 plus theta 2. Got it? So that is quickly here. Cos theta minus sin, sin and cos. So this can give you the orientation. So position and orientation you got quickly. Thanks a lot for this lecture, and next class we will be moving ahead with 3 degree of freedom spatial robot. We are done with planar now. We will learn what is a wrist, how that can be represented using DH parameter, and we will attach this wrist on top of the cylindrical robot only, and we will make a robot of 6 degrees of freedom cylindrical robot with wrist, and we will do one of the industrial robot, SCARA robot, if we get time. So that's all for today. Thanks a lot.